Hello everyone, in this video I would like to explain you about technology which is quite new in building service engineering, or it's quite rare. It's solar air heating, the use of solar energy for the direct heating of ventilation air. Have a look at the advantages and disadvantages of air as heat transfer medium. We all know that water is broadly used as a heat transfer medium in solar thermal applications. But what kind of advantages and disadvantages come into our minds if we use air instead? First, start with the disadvantages, because we all know that it's not as beneficial to use air as a heat transfer medium as water. First, it's the lower specific heat capacity than that of water. It's remarkably lower, 1.005 kilojoule over kilogram Kelvin is the specific heat capacity of air, compared to 4.19 kilojoule over kilogram Kelvin of water. And also the heat transfer coefficient with the air and the surfaces is remarkably less than between water and the surfaces. However, there are many advantages which we must talk about, because these are the points which make solar air heating quite a beneficial technology in the energy balance of a building. First of all, we don't need to take care of frost. Air does not freeze. Neither does it overheat in summer. It's the stagnation that we need to take care of and mitigate in systems for solar thermal systems with liquid heat transfer medium. However, here with air, this problem does not affect the system in any way. And also, it is endlessly available, which is quite important if you compare it with glycol as a solution with water, which can cost quite high amounts, so that we can protect the water-based system from frost. Have a look at the opportunities where we can use solar air heating, and I would like to reflect on various building types. If you think about a detached house, the more modern it is, the more likely it is to have mechanical ventilation, because the low energy consumption goes together with mechanical ventilation with heat recovery. However, the detached houses have very high comfort criteria, so it is actually not the best place to use large-scale solar air heating. Neither is an office building. Here you see an office building with a very high glazing ratio. The glazing ratio is something that can express the solar utilization of a building in the energy balance, how much solar gains it can utilize from the incoming radiation. And the higher the solar, the higher the glass surfaces are, the more intensive the solar utilization is. So in case of an office building, the solar air heating is not something that is the most useful in the building's energy balance. However, if you have a look at the third example for industrial buildings, the high mechanical ventilation needs and the low solar heat gains, in contrast with the office buildings, and the lower comfort requirements, make them ideal for the installation of solar air heating devices. Here you will see the system of an aerospace company, Bombardier Canadair, which has a very big solar air heating system, a transpired solar collector, the largest of its type in the entire world. First, have a look at modular collectors. They look quite similar to flat plate collectors. You see here in a few air ducts, canals made of the material of absorber. The air is streaming. The air is powered by a fan, which is supplied by a solar cell, so that this system can be made completely independent from the electric grid. This is also covered with a glazing pane to protect the absorber from the thermal losses, or at least to minimize them. It is possible to heat fresh air, and it is also possible to recirculate the internal air, so that higher temperature levels can be reached inside of a building. You can find such systems in alpine cottages. Here on the left, you see this solar air heating system with a PV cell, so that it's independent from the grid, and also in summer houses, making the summer house owner independent, and the summer house can be protected in this way during the winter period against some structural damages, because the interior of the building and the structure of the building can be all the year ventilated with warm solar heated air that helps prevent the structure from moisture in cold periods. If you think about PV cells, the PV efficiency is in best cases around 20% nowadays, and the rest is being transformed into heat. However, this heat reduces the efficiency of the PV cells further, and if you have a look at the relative change of performance as a function of the module temperature, you can see that every 10 degree of module temperature increase results in a decrease of 3% in the relative performance. This is why it's our interest to utilize this heat. It's not only the heat that we get in this way, but also the solar cells efficiency can be enhanced in this way, and it can be operated on a higher efficiency level. But let's come back to the transpired solar collector, which is actually the main target of HiSmart's second output, and in this part, the renewable energy module. The transpired solar collector is a collector that is built mainly for industrial buildings. As you see here in Canada, on the building of the Bombardier aerospace industry, you have here 10,000 square meters of solar collector area. And you might be wondering where the solar collectors are here. They are these gray area, which is the absorber itself, and it's covering vast proportions of the building facade. In the next slide, I would like to go into the details of its operational principle and the build-up. You can see here the absorber plate, which is a trapezoidal plate. It's based on some issues of stability and aesthetical reasons that it is trapezoidal and not a flat plate, and it's perforated all over its surface. The color is, of course, as dark as possible, but the house owner can choose in a wide variety of absorber colors. Obviously, the lighter the color gets, the worse the absorptivity will be. If you have a look at this cross section, this built up of the transpired solar collector, you can imagine the operational principle as well. You have the building's original wall, and creating an air gap, you are installing this perforated absorber onto the building's actual wall in a given distance, and in this way an air gap comes to be between the collector and the building's wall itself. This air gap is closed from all directions, and the point is that the air handling units which were withdrawing the outdoor air from the exterior simply will now withdraw this air from the air gap. However, the air can get into the air gap only through the perforations and not elsewhere, and in this way, the air entering the air gap gets heated up while transpiring this perforated absorber plate. And this is the way the transpired solar collector heats up this fresh ventilation supplier. You would be wondering how you can operate such a system without a glazing, which glazing would prevent it from thermal losses. However, once this absorber plate is transpired, you can keep the convectional losses minimal by ensuring a certain transpiration rate. This transpiration rate is between 18 and 180 cubic meters an hour over 1 square meter of absorber area. And this absorber must be transpired equally so that there are no dead zones and no areas without transpiration. And once this minimal transpiration rate has been ensured, the external warm boundary layer of the absorber plate is being sucked into the air gap earlier than convective losses would come to be from the external surface. This is why, if you have a look at the efficiency diagram of the collector, you can see that it depends only on the airflow rate and not on the temperature difference between the collector and the ambience, as it would be for normal collectors. So it is independent from the ambient temperature, and it depends only on the airflow rate. The more the airflow rate is, the higher the efficiency is because then you are keeping the collector plate on a lower temperature, reducing in even less losses, even lower losses, and this is why the efficiency increases with increasing airflow rate. You can see, however, some effect of the wind. Obviously, this system operates better in lower wind than in windy conditions. Let's have a look at the sources of benefits in terms of energy savings when you install a transpired solar collector onto your building. So first of all, there was solar air heating, quite obvious. We've been talking about this. Another one is interesting, whole heat recapture. Just imagine on the surface of the external wall where you install the transpired solar collector, it is recovering a certain amount of the transmission heat loss, because it creates an airstream in this air gap, and this heat which would go through the wall section normally is being recovered in this airstream, and it's being reintroduced into the building. So this is quite an interesting dynamic insulation system, the efficiency of which, or the effect of which, depends on various factors such as the transpiration rate and the solar radiation. Another thing is the building air destratification. It means, well, this is quite independent from the THC. It's just the effect of the distribution of the air inside of a building. The warm air would, from its nature, rise inside of a building and accumulate below the ceiling. One does not like this because in an industrial building, it's the lowest 2 meters that we use for occupancy, and this is why we do not want the heat go out of this zone and accumulate below the ceiling. And once we create an air distribution in a clever way inside of a building, we can mix up this distribution and create a rather more even temperature profile inside of a building. Here are some examples of transpired solar collectors all over the world. First and foremost, you will see here industrial buildings with low glazing ratios, low solar gains, large facade surfaces. You can see here too automotive industry buildings like in France and in Canada. This one is in Turkey. Here you can see it has 770 square meters of transpired solar collector area for the preheating of 63,720 cubic meters an hour of supply air. And when you calculate it for 1 square meter, it's 82.75 cubic meters in an hour over a square meter. So easy to be seen that this is between the boundaries of 18 and 180 cubic meters an hour over a square meter. In Hungary, two examples can be given in commercial buildings, in hypermarkets and an electronical store in Miskolc, Maglód, and Kecskemét. The picture below has solar ducts in case where you cannot install the solar collectors on a facade. You can create ducts on the roof. In certain very cold conditions, you can use two-stage transpired solar collectors with glazing. The higher part of the transpired solar collector is equipped with a transparent glazing, and this is why it can reach higher temperatures, and it's protected from the environmental loss where it reaches the highest temperature, and it's a second stage of the transpiration. Here you see another image of the duct type transpired solar collector, and the one below is the same system equipped with PV, and the PV itself has so much thermal loss that this loss can be utilized in a way of transpired solar collector air heating, further increasing the efficiency of the PV. Some interesting applications here in Germany in a monument industrial building for district heating. It is preheating the combustion air. Then in agriculture and animal breederys, you can use the solar collector, transpired solar collector, for the ventilation of the houses where you are breeding the animals, and reduce the energy consumption with it. in the timber industry, several drying processes can benefit from transpired solar collector applications, such as in agriculture. Here in this picture, you have an image of Caribbean tobacco farmers installing transpired solar collector. You might have come to the conclusion that this would be a nice system for winter, but no word has been said about the effect of the transpired solar collector on the building's energy balance in summer, and what happens in summer once we cover our buildings in a dark matte black plate. Doesn't it increase the cooling demand in a way that in the end we are going to lose the energy in summer, which we have spared in winter? There are two operations for summer for this solar collector, and I would like to show you these both. One is a night cooling technique. At night, every object radiates heat towards the sky, and which faces the sky once the sky is clear. And the transpired solar collector is also doing this, and the transpired solar collector cools down below ambient temperature, and with this radiation, the cold surface can cool the air further and ventilate the interior of a building with passive cooled air. This was the winter operation. The daily operation, the diurnal one, is when you just take the ventilation air from a bypass, because in summer you do not want to solar heat the exterior air, which is warm itself, but you want to bypass it, and then you leave your solar collector there on the roof of the building or on your building, wherever it is, on the facade or on the roof, and then it creates a natural ventilation inside of the air gap, and then it is going to just simply decouple the actual building from the absorber, which is hit by solar radiation. So one would first think that probably it's not so good having a matte black plate, but as it is perforated and it has a chimney effect in this air gap, it discharges this heat which comes to be around the collector, and it will shade only the building. And we have created a model, both mathematical and physical and experimental, for this, to prove this, and have a look at what we have figured out. So this discharging into the inside of the air gap. We had a measurement set up in Edirne, Turkey, of 5 square meters of absorber with an adjustable slope, and we were measuring solar radiation, ambient temperature, absorber temperature, air gap temperature, and backplate temperature. And here it's an energy balance of the heat flows on the transpired solar collector. And what you see here is we calculated the Q gain, which comes to the backplate from the solar radiation, and this could be expressed from this energy balance. And what we have got is this is one day that you see on the in the picture above, from 9 o'clock to 7 p.m. The yellow area shows the solar radiation. The red line is the absorber temperature, and the blue line is the backplate temperature. And up until 3:45, it was sunny without clouds, and after 3:45, some clouds arrived, as you can see. The collector's temperature, so the absorber's temperature, reached up to 75 degrees or even more. However, the backplate didn't reach higher than 45. And why is this? the case? It is because there's this decoupling effect between the absorber and the backplate in this ventilated air gap, and it's just naturally ventilated. So in this case, the fan was off. And what you see in the picture below is that you have the solar radiation here of many days, and the red area down there is the heat gain of the backplate, and it always remains below 200 watt over square meter, although in some cases the radiation, the global radiation measured in the plane of the absorber on the absorber reaches almost up to 1000 watt over square meter. In this thermography image, you see the discharging of the air as the higher sections are warmer than the lower sections, and this is one thing that proves this ventilation in the air gap. Here are some pictures about how the building's structure at night can be cooled down with ventilation air, and this ventilation air can be further reduced in its temperature by the night cooling operation of the transpired solar collector, the physical model of which is based on the long wave radiation towards the sky, as I have explained before. And here is some nocturnal thermal images showing that the collectors of different tilt cool down in different extent, and the flatter the collector is, the more it cools down. And also here in these sections you can see that the sections of the trapezoidal plate which see the sky, the clear sky in the most, so those which are not tilted cool down in the highest extent. Giving a short overview about transpired solar collectors, I would like to explain the advantages to you. It's a simple construction, therefore it has a low price among solar thermal systems, low operational costs and high reliability. Payback periods of 2 to 10 years have been defined earlier. However, the energy crisis of 2022 does not allow us to use such numbers any longer. In every case, it has to be redetermined. But it is very important to know about the buts. Its efficiency highly depends on the precise dimensioning and the accuracy of the operation, because the minimum 18 cubic meter per hour over a square meter have to be kept. Otherwise, there will be no air heating. And the building use is also an influencing factor. If it's changing, then it can change the whole operation, and these transpiration rates cannot be taken out of consideration. So this was what I wanted to tell you about the solar air heating systems. Thank you very much for your attention.